So I hear you're taking physics. I think that's great. I hear you're studying kinematic equations. That is also great. So in this video, I'm going to show you 3 kinematic equations that you're going to commonly use. So with that, we're going to talk about position, we're going to talk about displacement, we're going to talk about velocity, we're going to talk about acceleration. And I'm going to show you those 3 equations and where they come from in 1 dimension. Okay. So let's just get started. I have here a number line. It's actually a measurement of position. And so I have picked x equals 0 to be right here, and these are all in meters. So now let's say I have a person, and this person is standing right there. How do we describe the location of that person? Well, you could say that person's at x equals 2 meters. If I move this person over here, then that person is at x equals -1 meter. So this is position. X just tells us the position of this person at different locations. That's all it does. Okay, it's a way to describe the location. Now, imagine this. Imagine I had another axis where it looks like this. Right here, what's the position of the person? Well, according to this axis, that person would be at x equals 0, but according to this one, it'd be at x equals 2. So there's no universal origin. You can pick that to be wherever you want. And so the value of this doesn't really tell you too much. Because if you don't know the origin, you don't know where that person is. Okay, but that's position. It does have units, and we're going to use units of meters. And position isn't super important, except that I want to point out what it is not, and it is not displacement. So now let's not use this line. Let's use this one. And let's say I have my person, and the person goes from x equals 2. So we'll start off at x equals 2. We'll call that x1. The initial position is 2 meters. x2, the final position, is going to be 5 meters. So the person's going to go do. Now the person may or may not actually sing. Okay, it depends on the person. Some people like to sing when they move, and some people don't. But x2 is equal to 5 meters. How far did the person move? That's what we call displacement. And we'll represent this with delta x. And it's going to be x2 minus x1. In physics, we use the Greek letter delta to represent change in. So it really means the change in x. So it's the final x minus the initial x. So in this case, that would be 5 meters minus 2 meters equals 3 meters. And in 1 dimension, delta x could be a positive number or it could be a negative number. Let's say I go from here, x1 equals 2 meters. x2 equals -1. Then what would the displacement be? In this case, delta x would be x2 minus x1, which is going to be 2 meters. No, I'm sorry, -1 meter minus 2 meters. And that's going to be -1 minus 2 is -3 meters. So if you have a negative displacement, that means you're moving in the negative x direction. A positive displacement moves in the positive x direction. Okay, one other thing. Now, I could do this. What if I start from x equals -1 and I go from -1 to 5 and then back to 1? What's my displacement? Well, it doesn't matter what I did. All it matters is where I start and where I end. So this would be a displacement of 2 meters. Okay, so it only depends on the endpoints. So we got position and displacement. Now what we really want to talk about is how do we describe the motion of someone that's moving at a constant velocity? How do we describe that? You notice their position now changes with time. So we define the average velocity as the change in position over the change in time. So it not only depends on the displacement or how far they moved, but how long that took. Now let me go ahead and say there's a couple things. Speed, and then v equals x over t. These are important. First of all, this is wrong. A lot of times you see this velocity or speed equals rate or rate equals distance over time. That's bad. Okay, that's very bad. That assumes if x1 equals 0 and t1 equals 0, then this works, but only in that case. So don't use this. It's a bad idea. Okay, don't say speed is distance over time, and don't say velocity is distance over time. It's mostly wrong. Now, what about speed versus velocity? These two words are kind of complicated, and I think they can be used in a lot of different ways, and a lot of times people use them interchangeably, and I do often. Typically, velocity is a vector, and speed is not, but there's some other differences too. So for this case, let's just use these interchangeably. We can talk about speed versus velocity later. I'm going to try to use velocity as much as I can. Okay, but that's my average velocity. Let's calculate the average velocity for this guy. He's going to start right here. It could be a she. I don't know. At -2, and we're going to go 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 seconds. Okay, so I'm going to write down here t1 equals 0 seconds. I started the clock at 0 seconds. t2 equals 5 seconds. x1 is going to be -2 meters. x2 equals 5 meters. So what's the average velocity? Well, in this case, it'd be v average is going to be the change in x. So it's 5 minus -2 meters divided by the change in time, which is 5 minus 0. So this is going to give me 5 minus -2 is going to be 7 meters over 5 seconds. And then you can put that in your calculator if you want to. I just started using this calculator and I hate it. 7 divided by 5, enter. So 1.4 meters per second. That's my average velocity. Okay. Let's do something else with average velocity because it is kind of important. So let's say v average is delta x over delta t. Now, I'm calling this v average, but if they're moving at a constant velocity, then v average is the velocity. Okay, but this is important for something we're going to do later. So let me write this as x2 minus x1 over delta t. Now I'm going to multiply both sides by delta t. And I get x2 minus x1 equals v average delta t. Now I'm going to add x1 to both sides. I get x2 equals x1 plus v average delta t. And that is a kinematic equation. You may see this as x as a function of t equals x0 plus v0 t. That's the same thing, right? This is using different notation, where this is the final x, that's the initial x, that's the initial velocity. Sometimes we use O's for initial. And instead of delta t, we'll often assume t starts at 0. But this is only true for a equals 0 meters per second squared. Okay, only if the acceleration is 0. So there's a lot of different ways to write that, but the important thing is to say this is the final position, that's the initial position, that's my velocity, and that's my change in time. So we can use this to predict where something is in the future, and that's really nice. And let's actually do that. So let's say from before I have v average is 1.4 meters per second, and I want to find out where it is at x at t equals 10 seconds. So I can say x2 equals, well, where was it at x equals when it started? I had it at -2 meters, so it's going to be -2 meters plus the average velocity, 1.4 meters per second, times the time interval, which is 10. So I get -2 plus 14, 1.4 times 10 is 14. And that's going to, this is meters, and I have meters per second times 10 seconds is meters. And so this is going to be equal to 12 meters. So that's where it was. I can actually use that equation to find out where it is. Okay, let's go to, I'm going to need another, no, I got another sheet. Let's go to acceleration. We define acceleration as the change in velocity over the change in time. So just like velocity tells you how your position changes, acceleration tells you how your velocity changes. And so let's just say that this is going to be v2 minus v1 over delta t. And if I multiply both sides by delta t, then I get v2 minus v1 equals a delta t. And I add v1 to both sides to get v2 equals v1 plus a delta t. This is another kinematic equation, and I'll write these again at the end. So this says that if you know the acceleration of an object, how that object's changing its velocity, you can find the new velocity after some amount of time. And you'll notice it looks a lot like the position equation I have up here. That is an important equation, though. But what if I want to find out, what if I have an acceleration and I want to find out where the object is after some time? I want to do an equation like this, but for not a constant velocity, for an acceleration. Let's do that. So suppose I have an object in general. Let's say the acceleration is, I'm going to use that same equation right here. Right there, that I just had. So v2 equals v1 plus a delta t. But I want to find the position, so I have this equation. x2 equals x1 plus v average delta t. Now there's another definition for the average velocity. I can say v average is v1 plus v2 over 2. So let's suppose that I, instead of v average, I put in this. So now I get x2 equals x1 plus v1 plus v2 over 2 delta t. All I did was substitute v average as the initial velocity plus the final velocity divided by 2. That's all I did. Now let's use this equation and substitute in for v2. So I get x2 equals x1 plus v1 plus, now v2, I'm going to put this, v1 plus a delta t, all of that over 2 delta t. Now I'm going to multiply everything out over here. So I get x2 equals x1 plus, okay, so I have v1 times delta t over 2. And then I have another v1 times delta t over 2. So let's write that out. v1 delta t over 2 plus v1 delta t over 2. And then I have this one plus a delta t squared over 2. So this v1 delta t over 2 and v1 delta t over 2 is just v1 delta t. And this is 1/2 a delta t squared. So I get x2 is x1 plus v1 delta t plus 1/2 a delta t squared. This is a really powerful kinematic equation. This says that if I know the acceleration and the initial velocity and the initial position, I can find the new position. So I don't even need to know the final velocity. Okay, now we do have one more kinematic equation, and I need another piece of paper. What if I want to eliminate time? Okay, so let's write down this equation. x2 equals x1 plus v1 delta t plus 1/2 a delta t squared, a. And then I have this equation, v2 equals v1 plus a delta t. What if I want to eliminate time from these two equations? I'm going to solve, let's solve this one. I'm trying to think which way to do this. Well, let's say this. V average is delta x over delta t, which is x2 minus x1 over delta t. So that's my average velocity. I'm going to put in up here, this is going to be x2 minus x1 equals v1 delta t plus 1/2 a delta t squared. Right? All I do is subtract x1 from both sides. So this over here, I can put in for x2 minus x1. And that's going to be equal to v1 delta t plus 1/2 a delta t squared, all of that over delta t. And that's my average velocity, which is equal to v1 plus v2 over 2. So here you can see I can cancel the delta t, and this one is just delta t. So now I have v1 plus 1/2 a delta t equals v1 plus v2 over 2. Let's go ahead and multiply both sides by 2, and I get 2v1 plus a delta t equals v1 plus v2. I can subtract v1 from both sides, and this is not the best way to derive this. I didn't really think through it. I just wanted to let you know, but I will get there. So I get, if I subtract v1 from both sides, I get v1, and I'm going to subtract this from both sides, equals v2 plus a delta t. What? I knew that already. Okay, so now let's just, I'm trying to get to this. v2 squared equals v1 squared plus 2a x2 minus x1. That's the other kinematic equation, and I'm having a trouble deriving it right now, and I think I'll just stop and I'll derive that later. I'm trying to get in a circle. I'm trying to do it without too much trouble. I think I know how to do it, but I've done it before. Okay, well, I'm just going to leave it there, and I'll come back and rederive that. So then let me write the other kinematic equations just for completeness. I have this one, v2 equals v1 plus a delta t, which that can't be right. Then I have x2 equals x1 plus v1 delta t plus 1/2 a delta t squared. I feel like a failure for not fixing that, but I'll get back to it. Okay, so those are your kinematic equations. The most important one, this one does not have time in it, so if you don't know the time, use that one. This one does have the time, and this one just finds the velocity. Okay, I'll talk to you guys later.